In this video, we'll look at the zone theorem in high-dimensional space. In this problem, we have a set of n input hyperplanes, and they create an arrangement. And we have another hyperplane G, and we like to look at the complexity of the cells intersected by this hyperplane G. In other words, we look at the cells in the arrangement that intersect this hyperplane, and we add up the number of vertices, edges, and all the J faces contained in those cells. The theorem says that that number is bounded by n to the d minus 1. To prove this theorem, we'll use an induction. First of all, we're going to prove it only for the facets, or in other words, only for the d minus 1 dimensional faces of the zone. Assume this f function denotes the maximum possible faces or facets inside a zone of some hyperplane in d-dimensional space. We assume that we have shown that this f function is bounded by this O notation for all the smaller values of n or all the smaller values of d. To proceed with the argument, we use the following probabilistic method. We randomly pick one hyperplane and we color it red, and we color the rest of the hyperplanes blue. For example, in the picture, this hyperplane H is colored red and the rest of the hyperplanes are colored blue. Remember that a facet, is a d minus 1 dimensional object, and because of that, it lies on exactly one hyperplane. This means every facet will be either colored blue or red. If it lies on the red hyperplane, it will be a red face. Otherwise, it will be blue. We like to count the number of blue faces inside the zone of this hyperplane G. We'll do this counting in two different ways. One way to do it is just to use the fact that we have sampled H uniformly randomly. In other words, every hyperplane has equally likely to be red, and thus each hyperplane will remain blue with probability n minus 1 over n. Thus, if we focus on some facet of this hyperplane G in the zone of hyperplane G, that facet has the probability of being blue equal to n minus 1 over n. Thus, the expected number of blue facets will be this much. The probability times the number of the total number of facets. This is one way to count the expected number of blue faces. Another way to count the number of blue faces is using the other approach that says remove hyperplane H. We will have n minus 1 hyperplanes left, and all of these hyperplanes are blue. By induction, I know that I have at most that many facets inside the zone of this hyperplane G. Since all of them are blue, I have at least so many blue facets in the original picture as well. However, when I add the hyperplane H back into the picture, it could happen that this hyperplane intersects some blue face and cuts this blue face into two new blue faces, say F1 and F2. This cutting will increase the number of blue faces by some amount that we would like to bound in the rest of this argument. Before bounding this increase in the number of blue faces, let's look at the objects involved. Hyperplanes G, F, and H are d minus 1 dimensional objects. The intersection of hyperplanes F and H is a d minus 2 dimensional object, and the same with the intersection of hyperplane G and H, which is a d minus 2 dimensional object. The claim is that if H cuts F into two new blue faces, then this object, which is a d minus 2 dimensional object, lies inside the zone of this object, which is a d minus 2 dimensional object, where both of these objects live inside the d minus 1 dimensional space H. Okay. Let's see why this is true. The proof of this claim is relatively straightforward. The fact that both F1 and F2 are inside a zone of G means that I can connect F1 with a straight line segment to some point on G, and the same for F1. I can connect some point on F1 to some point on G with a straight line segment. Because of the cells in the arrangement of hyperplanes are convex, it follows that the convex hull of these 4 points will be inside the cell, and therefore it follows that I can connect some point on this object to some point on this other object with a straight line segment, and thus it follows that F intersection with H is inside the zone of G intersection with H. If we assume this claim, then it follows that the increase in the number of blue faces is bounded by this function. Because we're looking at d-1 dimensional space, restricting ourselves to hyperplane H, and we have n-1 hyperplanes, all the hyperplanes except H. So the increase in number of blue faces will be this much, and thus the number of blue faces is bounded by the number of blue faces from before plus the increase. If you place this inequality next to this value, we'll get that since the average value of B is this much and the maximum value of B is this much, it thus must follow that the average should be smaller than the maximum. Thus we get to this inequality. Solving this recursion might look a bit tricky, but we can use the following idea to do it. We can divide both sides of this inequality by n-1. I'll get here. And now we can rename this function as a g function. So we'll have g of n less than equal g of n-1 plus n to the d-3. And it's really easy to see that g of n solves to n to the d-2. And thus f of n will be bounded by n to the d-1.